In this example for section 14.2, we want to sketch the region R and set up and evaluate the integral. We have the double integral of the region of y divided by 1 plus x squared dA. R is the region bounded by x equals 0. Actually, that's a mistake there. That should be y equals 0. Y equals square root of x, and x equals 4. Let's go ahead and sketch the region and then determine when we look at this if it's would be better if the order of the differentials was dy dx or if it's dx dy. When you sketch the region, we have the line y equals 0. Well, the line y equals 0 is the x-axis. The line the curves y equals the square root of x, and x equals 4. So you can see those three do bound a region here. Now let's determine if we want to do vertical or horizontal rectangles. We can do either one based on the graph because it's both vertically and horizontally simple. So it may be best to look at the integral itself and determine would it be easier if the order was dy dx or dx dy. And since we have y, if the order was dy dx, we could treat y as a variable and this as a constant. And I think that would be a good approach. So if we determine the order to be dy dx, then the type of rectangles that we draw are going to be vertical rectangles. With that vertical rectangle, that long side there, that's your change in y going up and down, and that little change here is your dx. So our differential area the differential area dA, the area of that representative rectangle, is your length times your width, dy times dx. So let's determine our bounds of integration. For the bounds, when we look at the vertical bounds, your low and your high, your lower bound would be y equals the bottom of the rectangle, y is equal to 0. The upper is that top of the rectangle, and that top of the rectangle is y equals square root of x. So that's your upper bound. And then slide that rectangle all the way to the left to get your lower bound for x. Your left x would equal 0, and slide that all the way to the right to get your right bound for x, or your upper bound for x, which is x is equal to 4. So these are going to be our bounds of integration. The inside bounds for y would go from 0 to the square root of x, and your outside bounds for x would go from 0 to 4. Of the expression y over 1 plus x squared, and the order of the differentials is dy dx, because we drew a vertical rectangle. When we evaluate the inside integral, we're going to treat y as a variable and x as a constant. So we can write this as the antiderivative of this y divided by a constant is y squared over 2 along with that constant. So we can write it as y squared over 2, or we can bring that 1/2 out in front. So it's that constant, we're treating the 1 plus x squared as a constant. And we're evaluating this for the lower bound y equals 0 and the upper bound y is equal to the square root of x. Okay, when we evaluate the upper bounds, when y is equal to the square root of x, we get, and we square it, we get 1/2 of x over 1 plus x squared. And then when you plug in 0 for y, you get 0. So this is our single definite integral. You can use a graphing calculator using the integration feature to approximate this solution, or we can go ahead and use U-substitution. If we use U-substitution, I would let the denominator be our u. If we let u equal 1 plus x squared, then your du would have to equal 2x dx. Now we have the x and the dx. The only thing we don't have is that 2. We can put a 2 there as long as we put a 1/2 out in front. And also if we, let's go ahead and write this as an integral, this 1/2 along with this 1/2. We can write this as 1/4. And 2x dx is your du, and the 1 plus x squared is your u. And since this is now a single integral in terms of u, we should adjust our bounds. So again, looking at our original bounds for x, our left x was equal to 0. So if you plug that in to here, when x is equal to 0, we see that u would equal 1. And when x is equal to 4, plug in x where you establish your U-substitution, and you get 1 plus 4 squared, so your upper bound would be 17. So this would be the definite integral from 1 to 17 of du over u. This is a basic integration formula. The antiderivative of du over u is the natural log of u. So we can then write this as 1 over 4 times the natural log of u when we evaluate u from 1 to 17. We're going to plug in 17, and we get 1/4 of the natural log of 17. And then when you plug in 1, the natural log of 1 is 0. So our final answer would then be 1/4 of the natural log of 17.